In this video, we're going to derive the equation that relates equilibrium constants at different temperatures. So it's important that we understand that equilibrium constants are only actually constant as long as we're talking about that reaction at the same temperature. Remember that we are able to calculate equilibrium constant from standard free energy values, but the standard free energy value used in this equation here has to be the same temperature as the equilibrium constant. If you want to calculate an equilibrium constant at 25 degrees Celsius, then you can use the standard free energy change at 25 degrees Celsius. But if you want to calculate the equilibrium constant at 200 degrees Celsius, then you've got to figure out what is my standard free energy change at 200 degrees Celsius. And yeah, no, it's not perfectly truly standard anymore because it's not 25, but what is the free energy change for having standard concentrations and standard pressures and everything else except temperature be standard? That's what you need to do. Those two have to be the same. And the reason for this is quite simply that free energy values change with temperature, and they change quite dramatically with temperature. We saw in our earlier discussions this equation here, the delta G equals delta H minus T delta S, and that there were reactions that would go at some temperatures and not at other temperatures because changing the temperature so significantly changed the T delta S term that you would actually change the sign of the free energy change. And if you're going to change whether a reaction goes forward or backwards, you are absolutely changing the equilibrium constant for that reaction. So how do we deal with it if we want to talk about equilibrium constants at temperatures that aren't 25 degrees Celsius? Well, we have to make a couple of assumptions. We have to say that while we know that free energy changes wildly with temperature, we're going to assume that the enthalpy change for a reaction doesn't change too much. And the entropy change for a reaction doesn't change too much. And the big difference in that delta G equals delta H minus T delta S formula is the fact that we're changing T. Because if we can't make those assumptions, then nothing works. So we have to say that delta H at one temperature is going to be roughly equal to delta H at another temperature. And we have to say that delta S at one temperature is going to be roughly equivalent to delta S at another temperature, because otherwise we can't go anywhere. And so all the little 1 and 2 subscripts on these particular formulas are just referring to different temperatures. So this is at temperature number 1, and this is at temperature number 2. And at both temperatures, we should be able to say that delta G naught equals delta H naught minus T delta S naught, and that delta G naught is equal to negative RT ln K. We just put a whole lot of subscripts on to clarify which temperature we're talking about. So for each of those two equations, I'm going to isolate for standard entropy change. And the reason I'm doing that is because it's going to make the math work. And so if I take my first equation, I have the standard enthalpy change for the reaction, which we're saying is pretty constant, minus temperature number 1 times the standard entropy change, which we're saying is also pretty constant, is equal to negative RT1 times natural logarithm of K. And to isolate the entropy, I'm going to rearrange this equation. So I'm going to bring the RT ln K term over to the left and take the T1 times standard entropy change and move that over to the right. And then to isolate the standard entropy change, I'm going to divide both sides by temperature. And that's going to give me standard enthalpy change divided by that first temperature plus ideal gas constant times the natural logarithm of the equilibrium constant at that temperature is equal to the standard entropy change for that reaction. And I can do all of that again for the other equation with 2's instead of 1's, and that will get me standard enthalpy change divided by the second temperature plus the ideal gas constant times the natural logarithm of the second equilibrium constant being equal to the standard entropy change for the reaction. And since we have said that the standard entropy change must be assumed to be reasonably constant, I can therefore set these two halves of the equation equal to each other. And so that is going to give me enthalpy change for the reaction divided by the first temperature plus ideal gas constant times natural logarithm of the first equilibrium constant being equal to enthalpy change for the reaction divided by the second temperature plus ideal gas constant times natural logarithm of the second equilibrium constant. And I can therefore group similar terms together. So I put the terms involving the equilibrium constant on one side and the terms involving the temperature on the other side. And that's going to give me the standard enthalpy change divided by T1 minus the standard enthalpy change divided by T2 is equal to the ideal gas constant times natural logarithm of K2 minus the ideal gas constant times natural logarithm of K1. And you can see that there's some grouping I can do here. So that's going to give me the standard enthalpy change for the reaction times 1 over T1 minus 1 over T2 is equal to the ideal gas constant times the natural logarithm of K2 minus the natural logarithm of K1. And then if I divide both sides by R and switch what I had on the left with what I had on the right, then that gives me an equation that looks like this, which I can use my log rules to convert into the equation in the box, the Van 't Hoff equation. And this equation relates equilibrium constants at two different temperatures. You need to know the standard enthalpy change for the reaction, and you have 4 other variables. Typically speaking, you're going to know 3 of those 4 and be solving for the 4th. It is absolutely crucial that you stay organized enough that you make sure you match your K1 and your T1, that those go with the same temperature, and that you match your K2 with your T2. Because if you get things backwards, you're going to get wacky answers that don't make sense.